So one thing we can do is go over some of the more problem questions on the midterm. So we can look at the questions you guys had problems with on the midterm for a little while, or we can continue working on our game. So I have put on the student forum. Oops, wrong course. On the student forum, I have posted essentially the questions which people did the worst on. So the questions for which less than 60% of you guys got the answer right. I posted the question without the multiple choice things because once you have time now, you can really look at these questions and understand them. Yeah.
Is there any way to get our test back?
If you really, really want to know what was wrong, you can make an appointment and we can go over it one item at a time together. Yeah. Okay, so send me an email, and that'll be after the next week's reading week. Yep.
So it means that we won't get our physical test back?
No. I mean, your physical test is a red piece of paper with some black marks on it, right?
But
so.
I did circle the question sheet.
Yeah. No, if you're concerned that your Scantron sheet was read incorrectly, make an appointment, come in, and we'll hunt for that piece of paper. I have all of those white sheets that you guys have, and we can go through it one item at a time and see if the Scantron answers were recorded correctly. Okay. Well, there's a good chance that most of your mistakes come from these questions that are posted here. So have a look at those. And mostly they're easy to answer once you have a Python interpreter available. You just copy and paste the code and see what it does. So that gives you, the answer, which is true or false or yes or no. But you should do more than that, right? If you didn't get the question right or don't think you got the question right, you should do a little bit more than just copying and pasting it to know what the output is. You should try and understand why that's the problem. Okay. Yeah. So the one that I was very surprised by was the third question. That most of you got this wrong. 4 divided by 2 and 2 mod 3. They're both equal to 2. So the answer is true. And not less surprisingly was that only a quarter of you got the bonus question right, but it was a bonus question. So yeah.
What was the answer?
For the bonus question,
Yeah.
run the code and find out.
But I mean, like, in science.
What's that?
The science, there was like.
Which signs?
Square root 2 and pi.
Yeah. So the answers are square root 2 and pi. I don't know what that was on what choice that was on the Scantron, but and you can kind of deduce this maybe because this is squaring some value and trying to see if that's less than 1. This is squaring 2 different values and trying to see if that's less than 1. So you might guess, well, that means it's inside a circle or something if it's less than 1, and that has to do with pi and so on. So, I mean, I didn't expect a lot of people to get that one. And 25% is just a little bit higher than the 20% that you get by choosing at random, right? There's only 5 options. So that was as expected, but some were really unfortunate, like 11%. So 11% right is significantly lower than just guessing at random. So, okay, so do you want to go over these in class now? So put up your hand if that's what you want. Okay, and put up your hand if you don't want to do that. Okay, so think the people who want to go over them outnumber the people who don't, so we'll quickly go over these. What's 4 divided by 2? Okay, what's 2 mod 3? 2, okay? Because you think of this thing, so I suspect what's happening is some of you are confusing what the left-hand side and the right-hand side of the mod operator do. But think of 2 mod 3 the same way you think of 2 divided by 3. So really what you're doing is taking the remainder of 2 divided by 3. So 2 divided by 3 is 0 with a remainder of 2. So both of those things are equal to 2. And so the left-hand side equals the right-hand side. Okay. Do these two functions do the same thing? No. One of them has a bug in it. What's the bug? Yep.
The first one should always equal 0.
The first one will always be equal to 0. It starts with setting c equal to 0, and then after that it just keeps multiplying c times something else, but if you start with 0 and you multiply it by a whole bunch of things, it's still going to be 0 at the end of this process. So this first one will always return 0. This one is the standard factorial function, and at least for n bigger than or equal to 1, it will work properly, returning 1 times 2 times 3 times 4 times 5 and so on. Even if you're not sure if it works exactly correctly, it sometimes returns something other than 0, which the other one doesn't. So, so those are not the same function. Okay, this question here. So this is basically understanding what this list comprehension does. So in general, what do list comprehensions do? What's that? They're like a for loop. And what do they, when you evaluate a list comprehension, what do you get back? A list. Okay. So you get back a list. So not a string. And in this case, what is it a list of? It's a list of strings, right? So you'll get back a list that contains the string representation of y for every element y that appears in the input list A. Okay, so so I think the correct option there was A. This thing returns a list of strings. So it doesn't return one big string. It doesn't do anything else. It returns a list of strings. This code here. So it sets A equal to an array, a literal array that contains 1, 2, 3, 4. It sets B equal to A, and it changes the value of A at 1 to be 8, and then it prints B. So what gets printed? So what are the answers? 1, 8, 3, 4. Yeah. Okay. And you know, why is that? Right. That's because of this picture. This is A. It refers to an array or a list that contains 1, 2, 3, and 4. Then we create a variable called B, and we set B equal to A, and that just means take whatever is in A's box and copy it into B's box. Well, what's in A's box is a reference to this list. So both A and B refer to the same list. So when we say A at 1 equals 8, we're really overwriting this value here with an 8. And so now if we print B, we're going to print 1, 8, 3, 4. This, well, we're going to print, it would be the same thing if we printed A or B because it's the same list. Okay. All right. What about this next segment of code here? So the only difference is in this line right there. So what does that line do? Yeah.
Is telling you that you're assigning the reference to A, but the value.
Yeah. So the slice operator, this indexing operator where we use colons, this gives us a new list which contains, in this case, it contains all the elements in A, but it's a new list. So what we're assigning to B is this new list that we got, which is essentially a copy of all the elements in A. So the picture there looks very different. I closed it already. That A, you have A, you make a copy of A, and that's what B refers to. So A and B refer to different things. So here when I change A, it has no effect on B. B is still the list that contains 1, 2, 3, and 4. So any questions about those two? Okay. Then there's this little class hierarchy, which has it has place. Places have names. It has country. And it has city. Country and city are different kinds of places. And place implements the equals operator, and neither country nor city implements that operator itself. That means if you want to know if two countries are equal or two cities are equal or a country is equal to something else, what ends up getting called is this function in place here. Okay. And then we print, or we make three different objects. Canada is a country whose name is Canada. Canada is a city whose name is Canada with a K. And Can is a place whose name is Canada. Okay. So now, is Can equal to Canada? True. Why is that? So if I say is Can equal to Canada, that ends up calling the equals method for Can. Can is a place, and well, there's the equals method in the place class that checks if the name of one of the receiver thing on the left-hand side is equal to the name of the thing on the right-hand side. And indeed, both Canada and Can were created with the same name, so they'll evaluate to equal. Okay. Is that clear? All right. Now, are Can and Canada identical? So if I write Can is Canada, is that true or false? No. They're two totally different, two totally separate things, right? Canada is this country over here that has all this other information. It has a country code and a population. And Can is a place over here that all it has is a name. I mean, they're different kinds of objects even. So they're certainly not the same object. They're in different places in memory. So Can and Canada, one is not the other. Okay. All right. So that's good. We understand that part. Now, Canada is a city, and when we created it, we said, well, its name is Canada, its population is 100,000, and it's in the country Canada. Okay, so we create the country Canada, and Canada, is in the country Canada. If we look at what cities do when you initialize them, well, they have a name, a population, and a country. They use the name to initialize their superclass, which is place, and then they store the population and they store the country. So right now, after we do this, we've created this country called Canada and this city called Canada, And Canada actually has a reference to Canada. So the picture of that looks like this. We have this thing called Canada. It's a variable, so it's a box, and it refers to some country. That country has a name, it has a population, and I think that's all countries have, right? So that's what happens when we create Canada. Then we create Canada. So that's another little box, it's a variable. And Canada is a city. And city has a name. It has a population. And it has a country. So Canada refers to that thing. This name here is a string, Canada. This thing is an integer, which is, I don't know, I think 32 million. This thing is a string, Canada. And this thing is an integer, 100,000. Now what's this thing? It's a country object. So, I mean, the variables inside of objects are just like these. They're little boxes that can refer to things. So, you know, there's a little box inside this city. The name of this box is country. And what does it refer to? It refers to the same thing that this thing refers to. So it refers to that. Okay. So if I say Canada is Canada.country, the answer is true, because they both refer to the same country that we created up here. We only created one country, and well, so that they both have to refer to it in some sense. Okay, is that clear? Okay. So it's hard to tell from the multiple choice exactly, you know, which part you didn't get right. But this is, I mean, this is the question that seemed to be tough. So only 50% of people got it. So the two are certainly equal, well, because they are identical, yeah, and they're identical. So the answer is true, true. And here's another one. So we create a list with these three things in it: Canada, and Canada, and another empty list B, and we iterate through A, and we say, you know, for every element X in A, if it's not in B, then append it to B. Okay. And then the question is, well, how many elements are in B at the end of this? So if we look at the evolution of B, during this process, we have, you know, A has these three items, which are, you know, well, this one is a place. This item is a country. And the third item is did I get that right? City. So that's what A is. And now we do a for loop, and X takes on the values, all three of these values, one at a time. Okay. So B starts out empty, and then we look at, you know, the first value here. This is the first value for X that we consider, and now X is this reference to this place. And we say, If X is not in B, then append X to B. So at this point, B is empty. It's an empty list. So X is certainly not in B, so we'll append it there. So now B has one item in it. It's this place here. And this place has a name. It's called Canada. This is Canada. And this is Canada. Okay, so that iteration of the for loop is over. Move to the next iteration where now this is the value of X. So now we check, is Canada in B? So is this thing in B? So what do you think the answer is? Why? Well, I mean, B has one, I mean, B is a list, so we can ask if something is in that list. Yeah, it does. Well, I mean, you're looking in the list for something, you know, in the list that's equal to this. So I don't know. I don't think that's, yeah. It is what it is. I don't know. Is that valid syntax? Then it probably is going to test identity. If I had to guess, I guess it would test test identity. So okay, so one in A is true. One is in A. So why that doesn't seem to work? So what do you mean by is in? All one word? No, I don't know. I haven't seen it, but okay. So yeah. So anyway, what happens now is when you say, you know, is X in B, this goes through B looking to see if there's an element in there that's equal to X. So in particular, this first element here is a place whose name is Canada, and when you ask, is that thing equal to X, the answer is actually true, right? Because you know, so basically, it's gonna, the first thing it's gonna check is if B at 0 is equal to X, and in this case, the answer is true because they both have the same name, and equality is defined in this place place class as being two things are equal if they have the same name. So the answer is yes, it's in there, and so so it does not get appended. So X is X is in B. So so this thing is false. So it just does not get appended. And then finally, this is the new value of X. This thing goes through, it checks to see if this value of X is in B. So that means it'll compare B at 0 to X, which is the city called Canada. Those two names are different, so the answer is, well, no, it's not there. So it's not equal to B at 0, and there's nothing else in B, so it'll get placed in there. And so the second item in B will be the city Canada, and then that's it. We're done iterating through A. So the answer is that there's two items in the list B, because we're basically, this thing is avoiding putting equal items in the list. Yep.
Now, if you say X and B is a set, doesn't it look at the memory location?
Yeah. So that was the tricky question. No, that's actually, I pasted the wrong question here. So that was this question, which looks like, I wonder if I'm allowed to edit this. I don't know, maybe the question was like this, or maybe it was B is equal to set A, but it does the same thing anyway. And then, so then the question was, well, what does that do? How big is A or B or whatever it is after this thing executes? And the correct answer there is we can't actually know. And that's because sets, if you want sets to work properly, you have to implement both the, and you've changed the equals method, then you also have to implement this hash method. And we didn't do that for Canada, or not for Canada, for place, and so actually sets don't work properly. You shouldn't store these things in sets. So there may be 3 items, there may be only 2 items if it happens to get lucky, but and it may run one time it has 3 items, another time it has 2 items. We really don't know. This was a tricky one. So here's this code for that says it will return a list having only the values x, where minus x is also in the list. Let's save this so we can see it a bit better. And so the question basically is asking is this comment accurate? Is this really what this function does? Yeah. The answer is yes. And what this thing does not promise you is anything about the ordering of the elements in the list. So the sort of tricky thing is you may have seen this minus x and said, no, it doesn't return x, it returns minus x. Or it doesn't put x in the list, it puts minus x in the list. But it only does that if minus x is in the list. So it actually is giving you a list with the same elements in it. If and only if minus x is in it. The comment is somehow hiding something, which is they're not in the same order that they occurred in the initial list. Okay. These 2 functions, anonyms 1 and anonyms 2. So each one takes a big list of words, let's say 100,000 of them, and converts that into a set called the word set. And one of them goes through and checks if the reversal of each word is in the word set. So it goes through the list of words and does that. The other one goes through the words in the word set and checks if its reversal is in the word list. So which one of these is fast and which one of these is slow? Yeah. Yeah. So the key here is sets. There was a whole assignment sort of about this. Sets are very fast to add things, remove things, and check if something is in the set. So what this thing here, which is going to happen 100,000 times, will be very fast in this first version, and it will be not very fast in the second version. So in the first version, basically this happens in a few microseconds. It's independent of how many elements are in the set. This one here actually has to go through and look through 100,000 words to check to see if it's in there. So it goes through a list. So the first one is really fast, and the second one is actually really slow if you have 100,000 distinct words. Now what most of you got right is if you have only 100 words, then both of them are fast, because even though the second one has to look through 100 times 100 words, that's only 10,000 words, which is still really fast, but 100,000 times 100,000 is about 10 billion or so, so it's not, that takes time. And then the last question, question 25, is actually an implementation of something called the Monte Carlo method. And the Monte Carlo method is kind of cool because it's a way of calculating values without knowing much about them except some function that defines them. So maybe the easiest one to see is this bottom, the second one here. So this takes two random values between 0 and 1, and it squares them, and it checks if that's less than 1. So if we look at that, so it takes two random values. Let's call one of them y, and let's call the other one x, and they're between 0 and 1. So here's 0, 0, here's 0, 1 up here, here's 1, 0. So what we're basically doing, since we take two random values, it's like we put on a blindfold and throw a dart into this square here, this 1 by 1 square. Okay, so it could be equally likely to be anywhere in this square. And now we do this check, and we ask if x squared plus, so if is x squared plus y squared, is that less than 1? So sometimes that's true, and sometimes it's false. So when is it true? Yep. When x squared plus y squared is smaller than 1. And what does that look like in this picture? Yep. Yeah. So x squared plus y squared, that's like the distance squared, right? And in particular, if the distance is smaller than 1, then so is the distance squared. If the distance is bigger than 1, then so is the distance squared. So that's really asking, is the distance from this point here to the origin, is that smaller than 1 or not? Well, so this is a distance that's equal to 1. This is a distance that's equal to 1, right? And actually all the distances that are equal to 1 form a circular arc like this, right? That, you know, are you within distance 1 of the origin is really asking, are you inside a circle of radius 1 centered at the origin? Okay. So this thing, you know, will evaluate to true or 1 if you're inside this circle here. Okay. Now, what's the area of this square, this 1 times 1 square? It's not a trick question. A square of side length 1, so a rectangle, a 1 by 1 rectangle, it has area equal to the width times the height, so 1 times 1. So the area here of this whole square is 1. Now, what about in here? So what's that area? Yeah, so the area of the whole circle, this is a circle of radius 1, so the area of the whole circle is pi times the radius squared. The radius is 1, so the radius squared doesn't matter. So this whole thing is area pi, and we're only looking at a quarter of it. So this orange area is equal to pi over 4. Okay. So we throw a dart in this region that has area 1, and if it happens to land in here, then that counts as a 1. So what's the chance that it lands in here? Well, it's this orange area over the total area. So it's pi divided by 4 divided by 1, or if you like, just pi divided by 4. So this says, you know, if we throw one of these darts, the probability that it lands inside the circle is pi divided by 4. Okay, so somehow the pi shows up in here, and then if we go back and look at the code, well, we do this n times, and at the end of this, we multiply by 4, so now it should be, it's not pi divided by 4 anymore, it's just pi, and then we divide by n, and so at the end, the number of these darts that we expect to land in the circle, and well, the number of darts that we expect to land in this circle will be pi divided by 4 times n. We multiply that by 4, now it's pi times n, and now we divide by n, so it's, the result is pi. So I didn't really expect anybody to, or not too many people to work through all that, but the sort of hint is if you recognize this thing as being, you know, that the distance from the origin is less than 1 means you're inside a circle. As soon as you think of circles, you think of pi. Okay. So there's your first program maybe for calculating the digits of pi. Yeah, it's a really bad one, by the way. No, between 0 and 1. Yeah.
So if it's between 0 and 1, and it's going to be a decimal at 0 points.
Yeah.
If you square a decimal at 0 point, it gets smaller.
Yeah.
So is it, because how I did this, I just said if you get a number that's a decimal and you square it, it's going to be twice as less than 1. Because if you have 0.3, you square it, 0.03.
Yeah.
So if you're going to try n times, you will probably get x every n time you try it.
You will probably get x.
X for x in range, and if every n time you try, you go through that list, you get x every time. Because you always get a random number squared that's going to be less than 1.
Well, no, only if you square it. I mean, you add 2 of these things and check if they're less than 1.
Starting from the first part, when it has land x for x in range, and if 2 times random square.
Oh, this thing here.
Yeah.
Okay.
So if we pick a base case like 0.3.
Well, I mean, just let's figure this out. When is 2 times x squared less than 1? So 2 times x squared is less than 1. That's the same thing as writing x squared is less than 1/2. And that's the same thing as writing x is less than the square root of 1/2, which is equal to 1 over the square root of 2. Okay? And then the last step in that thing is to multiply by 2. So whatever that, I mean, we do this n times, so we're now going to have something that looks like 1 over square root 2 times n. So that's about the number of the length of this list, should be about that much. And now we multiply by 2 and divide by n. So times 2 over n. This n and this n cancel out. And we're left with 2 over root 2. And what's another way to write 2 over the square root of 2? That's just the square root of 2. Okay. So again, we get something that gets, the longer you do it, the closer and closer you get to square root of 2. So both two numbers that are, irrational, so they have, infinitely many digits if you try and write them out, but you can approximate them using little tricks like this. So that's actually called the Monte Carlo method. When you take a statistics course, you may learn about that method. Okay. So any questions about those? So those won't have hit all of the maybe mistakes that you made, but this is a big set of them will be hit by this. And if you're a little bit shaky on this now, go back to this post and read this second line here. So questions like these, or these questions, will appear on the final exam. I don't do these things because I like to torture you. Maybe the last one was a little bit of torture, but again, that was a bonus question, so you didn't lose anything by not getting it right. I do these things because they're important, and I really want you to learn them. And if you don't learn them, you'll be punished again on the final exam. Yeah. No, I don't want to do that. You have you have last year's midterm that's blank, and it's not so different from this one. Reason I don't want to do that is because then every year I have to create a whole bunch of new questions for the midterm. Every time you create a new question, there's a chance it contains a mistake. Every time there's a mistake, there's 50 people in the class who ask me to come and explain it to them during the exam. There's a lot of running around, so I'm a little bit guarded with my midterms. So here you have the problem questions from this midterm. You have last year's midterm, so that's a pretty good selection to study from. And I think, I don't know, it's up to you to tell me whether this is true or not, but was last year's midterm a fairly good representation of what this year's midterm looked like? No. Okay. I'm surprised by that. Now, the last year's people did not have any midterm to study from. So there were questions on both midterms, right? Some of the questions were identical. So people last year didn't have any of that going for them. So I don't know. Maybe it was easier. I don't think so because, well, I don't know. I wouldn't have thought so, but who knows. In any case, the marks on these exams are not terrible. I mean, the standard, the median mark is about a C, which is about what I expect in a first-year course like this. Yep.
It's written something about midterm corrective something on the thing. Is there a bell curve in this class?
No, it's just that the raw stuff that came out of the Scantron stuff was out of 25. So this thing is derived from the Scantron results, but it's divided by 24 instead of 25. Yeah. So so there's no bell curve, and if you did better on the midterm than someone else, there's no, that your mark is still better than theirs. There's no weird adjusting of marks where some people who did worse suddenly do better or anything like that. Okay. Final exam will be multiple choice, and so time didn't seem to be an issue. Is that right? Okay. Maybe a little more time would have been better. Maybe you should have taken more time. So that wasn't an issue. And so the final exam will basically be, well, this is worth, I think this exam was worth, what was it, 20% of your mark? Yeah, and the final exam is worth how much? 40. So the final exam will be twice as long. So each question will be worth the same amount as these exams. So will it be what? No, there'll be, you know, if there was 25 here, there'll be 50 on the final, roughly. Does that mean there'll be 2 bonuses? Sure. Yeah. Remind me of that. No, it's still going to be multiple choice. Definitely on the final it will be multiple choice because TAs are all done by the time final exams are done, so there's no TAs. And there's not a chance that I would ever mark 325 exams by hand. That it simply wouldn't get done in time. Sorry. Okay, so we're okay with that? Some of you are not totally okay with it maybe, but not that happy about how things turned out. But again, this is still really early on. There's a chance to improve things if you did poorly. And if you did, don't just grumble and get mad about it, but you know, try and understand what was wrong so you don't do it again. So one thing that I can tell you that has happened in previous years is I've put questions both on the midterm exam and on the final. So some of the questions on the final I can almost guarantee will be the same as the ones on the midterm. What I find a little bit counterintuitive and a little troublesome sometimes is the success rate on those questions is often worse on the final than it was on the midterm. So people are sort of going backwards. They're not getting better, they're getting worse at some of these questions. I guess the explanation maybe is that maybe this material was more fresh in your mind for the midterm, and then later in the semester it became older or you forgot it. But let's try not to do that. Yeah.
We're not going to get a final exam practice test,
No, I don't think so. Yeah, I don't think so. It would be nice. We'll see when they ask me to submit my final exams. If they ask me to submit them in like 2 weeks, which is common, so you know the exam is sometime in December, but very frequently I'm asked to submit them in the middle of November. Then I probably won't have time to make an entirely fresh new final, which means I don't want to show you the old final. If they ask me, if they give me more time, like till beginning of December to submit it, then there's a chance that I could release the old final. Okay. And you know, maybe another way to do it is to, something that I can do is provide questions which are not multiple choice questions, but are related to what is on the final. Because these multiple choice questions, they're actually a lot of work, because you have to be extremely careful that there's not more than one correct answer, and that there is one correct answer, and it's really easy to screw them up. And so it's easy to just make up questions and say, what does this do, what does that do? But to have, you know, reasonable multiple choice questions actually takes a lot of work. But it's less work than marking 320 exams. So, okay. So last class we had been working, so we're not going to have time to do too much, but a little bit. We had been working on this game. And calling it a game is a little bit much. It's just an ant who walks around and dies. So we got a lot of the logic done. The ant was smart enough to locate the nearest piece of food and walk towards it. And we laid down some poison, and if the ant walks over the poison, then it dies. And now that we wanted to turn this into a game where your job is to get rid of this poison before the ant gets there, And maybe there's going to be some kind of, it remains to be seen, but maybe there's a little bit of skill involved in this game because, you know, if the ant's moving pretty quickly, and it is here, then there could be some pre-planning involved, right? Like, yeah, you want to get the stuff directly out of the way of the ant, but once it gets to its food, it's going to go to the next nearest thing, and maybe you should predict what that should be. So let's continue that thing. All right. So the game is still not playable, and to make the game playable, we want to have some way of removing this poison. So I guess the interface is going to be that you click on a piece of poison to get rid of it. And well, so remember in this whole Pi game setup, we work with events. So where are we? We work with events. So there's this event loop. Right now, there's only two kind of events, which is the tick, the refresh event, which does several things. It redraws the screen, and it does any movements of the ants and checks if the ants landed on the poison, and checks if the ant reached the food, does all of that stuff. And then there's the quit event when someone clicks the close button on the window. And so now we'd like to capture another kind of event, which is mouse clicks. And we won't be too fussy about what kind of mouse clicks. Basically, when the mouse button goes down, we'll treat that as the user trying to do something. Okay. So mouse click events have a position. It's called POS. So they have a thing called a position. Or an attribute called a position. And so now this is what happened. The user clicked on that position. We'd like to know, does that get rid of some of the poison that's on the screen? So how do we do that? Okay, so let's so there's several things of poison, right? So they're stored in a set called poison. And so we'll say for P in poison. So poison is a set of these poison game items, and we'll iterate through that set. And actually, I'm going to do something that looks a little bit strange here. And before I iterate through that set, I'm going to turn it into a list. And I'll explain why in 1 second, why this is something we need to do. But for now, let's just leave that for a second. If I forget to explain it, someone remind me. All right. So now we're going to go through each poison item, and we're going to check if well, we want to know if someone clicked somehow on the poison or close enough to the poison or whatever. So we'd like to know something about P's position versus the position that the event happened. So the event happened on that's where the coordinates of the mouse click are, and P's position is the position of the center of this drawing of a piece of poison. So a decent way to check this is to maybe check if the distance is small between those two things. And you know, maybe a reasonable test is P has a size, which is the maximum of the width and height of its image. And so if I say less than the size divided by 2, that sort of means I'm in a circle around the center of that thing that contains the image. Right? So just graphically, this is the picture of the poison. It's drawn right at the center like this. The size is given by the maximum of the height and the width. The picture is roughly square, so that's good enough. And so basically, if the user clicks anywhere in there, then we'll treat that as clicking on this thing, right? Because that's the radius of that thing. So not bad. I mean, the images are rectangular, but they're actually transparent in a lot of places, so they're more triangular. So actually, it probably looks more like this. So we might run into some issues, but we can fool around with that a little bit. Okay, so if the user clicks on the poison, we would like to remove it. So we'll say poison, which is a set, remove P. Anything else we should do? Yeah, we don't want this to become too easy, right? If they're really quick and get rid of all the poison right away, then they're done. The ant just walks around eating food forever. So we could place a new one. So poison.add self.new poison. And if you remember from last class, this new poison was a method that we wrote that that chooses a position for a new piece of poison that's not too close to the ant. So it should be fair to the user, somehow not fair if the new poison appears directly in front or on top of the ant. Wouldn't give you a fair shot at it. Okay. All right. So back to this thing here. Why did I convert this thing into a list? Well, it turns out that if you're iterating over something, which is what we're doing here, you know, when we say for P in this, which is this thing which is now a list, it's not a good idea to be changing it while you're iterating over it. That tends to break things. So in particular, if you're adding and removing things while iterating, that can cause a problem. And so basically what we do is we take a copy of all the poison that happens to be here right now in this set. That's the thing we're going to iterate over. And the thing that we're changing is the original set. So we don't want to be iterating over this thing which we're adding and removing items to. Because, for example, if it's not even clear what should happen, right? If I iterate over a list of poison things and halfway through iterating I add something to the list, should that be something that I iterate over now or not? I don't know. It's not clear, right? Maybe I've already skipped over it or maybe I haven't. So better just not to fool around with that. Okay, and so let's see if that works. Poison is not defined, and it's not defined because it's self.poison. Are there any other selves that I'm missing here? I don't think so. Yeah. Okay, so that seems to work. So clicking on these poison things seems to get them out of the way. And just to test this a little more carefully, we could, for example, just stop the ant for a second and see how we're doing with this. So clicking, 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 click, there we go. Clicking, clicking, clicking. So, and we can kind of sneak just on the corner and it doesn't go, but it's not bad. So you have to click sort of, you know, close enough to the skull. If you really cared, you could do this a little more carefully and actually see that you're right clicking directly in the triangle, but that'd take a little bit more code. Okay. All right, so we've got that going. I guess something we could do is maybe add a bit of sound to this. So maybe a game over sound. Self dot. And what's it called? Buzzer. So sounds are like other things, like images. You usually want to load them once at the beginning of the program and just reuse them. So you use Pygame's mixer module, you create a new sound, and in this case I'm keeping my sounds in a directory called sounds. Okay, so we load this thing. When we initialize, we've now loaded this sound called the die sound. And we'd like maybe to play that when the game ends. So where does that happen? When we change the game state. So we're looking for this game over state, and here's the place where we change the game state to game over. So we'll say self.dieSound.play. Oh, we forgot to reanimate the ant. Back to life, only to kill him. Okay, so we have that going. So one other thing that I'll show you is something that actually makes a big difference in terms of a game being more fun or interesting or playable, and that's a soundtrack. So So here's a very short sound, and you can find lots of these things online. I think there's a pointer to them, maybe not to one of these sites. So just look for sound loops, because usually you want a loop and not a giant thing as a soundtrack. So they're usually not too long, and they're designed so that if you play them repeatedly, over and over, it sounds like someone is just playing, like, see, it ends abruptly there, but if you started that loop again right at that point, it sounds, you can't tell that it's started there. So guitarists and all kinds of musicians work really hard on these things with audio editors to line up the ending and the beginning so that they're perfect. So let's make use of that thing. So when we initialize our game, we have already loaded a sound. We'll do it again. Self.soundtrack is load sound. And now we go look at the Pygame documentation. you know, always look at these kinds of things. So sound.play, so when we load a sound, we get one of these sound objects. If we look at the play method, it has a bunch of different arguments that all have default values. And the first argument is loops. How many times we would like to play this sound over and over. And we can set it to -1, which means play it forever. And something else that's a little bit nice is there's also a fade, which is the number of milliseconds it takes for the sound to come up to full volume. I think max time 0 does nothing. Okay, so let's try. So we want to play forever. That's what the -1. -1 loops is forever. We don't, the max time we don't care about. We'll set it to 0, which means no upper limit on how long it should play. And let's fade in over a period of 2 seconds. There we go. Yeah, that part's not, the buzzer is not the best sound effect. I would maybe hunt around a little bit more for something like that. But I recommend, actually, for all your games, find some loop that sounds nice and use it. Okay, that's good. What else could we do now? There's a few things we could do to make this game better. What are the standard things that we should do that this game doesn't have yet? Play again without closing it? Okay, so play again without closing. Let's think of, like, it's good to have really dumb interfaces for things, and so I think we could live with a one-button interface. We have one button for getting rid of poison. Same button could be to play again, right? So let's see if we can get that working. So if the event type is mouse button down, and actually this is something we should also take a look at. You may not have expected this, but okay, die. Even after the game is over, we can keep clicking on these things. So those are the kinds of things to look out for if it matters to you. Right? It's just the way we did our game states. We never said you can't click on something if it's in the game over state. So if we don't like that, we should maybe. If the event type is pygame, mouse button down, and self.state is equal to game.playing. So if we're playing the game and you click the mouse button down, then we should do one thing. On the other hand, if it's game over, then maybe we can restart. And so what does restart look like? Well, we have to basically get everything going again. So we'll do something like take all this initialization code, starting with creating the ant, the food, the poison, choosing the food, all of that. We'll call that restart. And if we're lucky, that will just work for us. Because I didn't say restart, it should have been, always a mistake, self.restart. If you spot one of those before I do, please tell me. So now I click on the screen, starts over. What did we forget to do in restart? Yeah. And how do we make it start running again? Yeah. So the problem is in restart we forgot one thing that init does, which is set the state to playing. Never dies as quickly as you want him to. Okay. So now restart. Yeah. It's actually not that easy of a game, especially with a, actually maybe with the pen it's easier. Maybe it's too easy. But there is actually a little bit of, you need a little bit of foresight. Okay, so we're getting somewhere now. What else do games have? Scores. Okay, so we now seem to be doing everything in restart. So we'll set the score to 0 when we restart. What else do they have? Lives. Maybe that's not one we want to do in restart. In fact, maybe we would like a really, really restart. Let's leave that like that. So lives and score. And if we're going to do lives, then game over. We shouldn't necessarily go to state game over. We might want to do something like self.restart. Well, let's say if self.lives is bigger than 0, .lives minus equals 1, and restart. And otherwise, we're out of lives. Then we go to game over. So I just died once there. Let him die. Died twice. And game's over after 3 deaths. Okay, so we're getting there. Maybe the only thing that's missing is well, displaying the score, displaying the lives. That would be nice to know for the player, and some level of difficulty that increases, because I think playing this for a while I could quickly get to the stage now where I could play forever. So enjoy your reading week.
Is our next assignment going to be making a game?
That's probably going to be 2 assignments from now.